AI in action, and you know that we're experts because a couple of things. We're on a stage and we have beards, so it seems obvious. My name's Matt Williamson, and sitting beside me is Dustin Reagan. I'm the CEO at Clever, and he's the guy that's actually doing the work that we're going to talk about today, so he's the guy who it kind of matters that he's here today. We're a software company here in Oklahoma City. We do custom software for all kinds of people all around the world, and what we're going to do now is a demonstration of some simple AI stuff that is off the shelf. And so, where the hell do I hit? Yeah, do that. I'll just yell next from now on. So, I bet everyone here knows what AI is, right? Everyone's got it on their phone. We utilize it every day, all day. But if we're going to define it, I suppose we could say it's a computer system's ability to perform tasks that normally require human-level experience or intelligence. So things that we are super used to now in our world are little silly things like if you use Gmail, it will try to proactively help you finish the next sentence, right? And it's really good, and it even learns, like I have a tendency to say things like badass in an email. And so now if I start typing BA, Gmail's like badass, and I'm like, yeah, badass. So hit tab and move on, which I love. I bet everyone here's used some navigation when they're driving somewhere, or they've used Uber or Lyft, and there's so much machine learning built into those platforms that it kind of boggles the mind. But we're all used to them now. This one's kind of my favorite lately, this little tiny example. I know this is the way it works on an iOS phone. I'm guessing it's the same way on an Android. Didn't have an Android to grab with. If you go into your phone on an Apple phone and you look at your Photos app and you can start typing in weird things, you'll see that it has used machine learning to categorize your photos for you without you doing it. You didn't have to train it. You didn't say, this is my cute puppy, this is my house, right? It just finds these things for you. And then another one that we're all used to is just your smart assistant, whether it's Siri or Alexa or just screaming, hey Google, and it knows all kinds of things about your day and the weather. And like if I say good morning to my Google in the bedroom, it knows my routine. It tells me how long it takes to get to the office and what the weather's like, and it'll tell me how many emails I haven't answered that morning, right? So the thing about AI and machine learning specifically is that it can do things that beforehand we just kind of thought were almost unattainable. So for instance, in this particular thing that Dustin and I are both kind of geeking out about, how many of you have ever played Chinese Go? Wow, there's like 3 of you, thanks guys. So the thing about Go is it's really freaking hard, and in the 11th century, a Chinese philosopher and mathematician figured out that there are 10 to the 172 power moves available in Go. And that's crazy if you realize that there's only 10 to the 80th atoms in the universe. Like, it's not even astronomical, it's a number I can't even get to. But now an AI can beat a Go player so fast and so often that since 2017, I think it is? 2016, AlphaGo has not been beaten. So, it's amazing. So this says AI finding cancer, and we should probably roll it up to AI in the medical field, because the stuff that data can provide to an algorithm is kind of mind-blowing. If you're an oncologist and you've trained your entire life and you think you know exactly what it looks like when such and such happens, that's great, but now you can put the data behind every oncologist who's ever recorded data. And so the AI can find cancer and or other maladies so much better than humans can. It's just
in a lot of cases.
In a lot of cases. Tesla, anyone been in a Tesla and just like taking your hands off and trusted to God that this thing was just going to do its thing, and it does, like it drives you where it's going to go, and it changes the way you think of driving. And even not in a Tesla, like I've got a Subaru, and the Subaru's eyesight just does things. It keeps you in your lane, it does the reactive driving. If someone gets in front of me, it just knows to slow down, and if they get out of the way, it flies up past them, and it's amazing. So this is one of my favorite examples of AI in action. National Geographic has been doing this particular thing in the Himalayas for a long time, where they have cameras all across the Himalayas, and those cameras are on a trickle feed to send in their data. And so humans would sit down in a room like this and just start pouring through these photos looking for snow leopards. And it was good, but it would take, hundreds of thousands of man hours to look at hundreds of thousands of images. So they worked with Microsoft, they trained some AI, and now they're able to find snow leopards in photos that just no human would ever have seen. It's fascinating to watch. So that leads into what Dustin built for us as a proof of concept, and I'm gonna let him explain.
Before I go through my demo, I just wanted to give a really brief base level, kind of surface level description of how most modern, I'd say not most, like almost every single modern image or visual-based machine learning system works these days. It's, for the most part, based on a technology called artificial neural networks, aka deep learning. That's kind of the buzzword that you've probably heard these days. But they, as the name suggests, they are inspired by biological systems, by the brain, but it's, I'd say, very roughly inspired by. Basically, like the brain, the basic processing unit is a neuron, or as usually referred to as a unit in artificial neural networks, and these units take an array of inputs and they send an array of, or they send an output, and so they're very, very simple. So it's basically a network of very, very simple computations, but together, there's, I mean, in modern systems, there's anywhere from hundreds to hundreds of thousands of individual units communicating with each other. This is a diagram of an individual unit. The way it works is really simple. You have, again, an array of units, or an array of inputs, and those inputs are just numbers, just numerical values. And each input has an associated weight, and those weights are kind of the fundamental important part of an artificial neural network, because those weights are what change during the training process and allow learning to occur. So what happens is, it's a really simple calculation. Each numerical input comes in, it's multiplied by the weight, then those multiplications are summed up and sent through what's called an activation function. Don't worry about that. It's usually some really simple function that's like, if the summed value is less than 0, just send 0. If it's greater than 0, just send whatever the value is. Okay, and so that value gets sent on to other units that this unit is connected to. And so they're typically connected in what are called layers. So in the case of an image-based neural network, the input layer takes the raw pixel values from the image. So, digital images are essentially just an array of numbers, right? Each pixel is a number. So those pixel values come in, those simple computations happen, and those units send their simple computations as inputs to the next layer, and so on, until you get to the output. So in this example, we're just going to say, okay, we have a network that learns to distinguish between cats and dogs, right? So you're going to have, to train it, you're going to need a bunch of pictures of cats and a bunch of pictures of dogs, and they have to be labeled pictures. So first of all, you have to have a person who has pre-labeled these pictures. Like, this is a picture of a cat, this is a picture of a dog, this is a picture of a cat, so on. And the output of the network is going to be 2 units. One unit which we arbitrarily decide is the cat unit, and one unit which we arbitrarily decide is the dog unit. And once you show the network an image, you feed those raw pixel values in, it does its computations. Each of those output units is going to end up with their own output values. And we say, okay, if the cat unit's output value is bigger than the dog unit's output value, then the network has decided that the image is the cat, right? And so when you train one of these, you start out by initializing all the weights in the network just essentially randomly. So that when you show it a picture of a dog, it's going to have about a 50% chance of getting it right. You show it a picture of a cat, it's 50% chance. And then you start showing these pictures, and these images to the network. If it gets it right, you don't do anything, you don't change anything. However, if it gets it wrong, it uses a really simple process called backpropagation to essentially step backwards layer by layer through the network. And it basically figures out, says, okay, you said this was a cat, but the picture was a dog. How could I change the weights slightly so that it's more likely to get the right answer? And then you just very gradually, slightly change the weights through the network. And you just have to repeat that process hundreds of thousands of times until it finally starts getting things right. So again, it's actually like a pretty simple process.
He says simple.
It's not complicated. You can at least grasp the basic concepts. It's just bit by bit improvement, essentially. Right? Tuning, right? So again, like I mentioned, these networks are almost always organized in layers of units, and the term deep learning comes from the fact that in kind of the early 2000s there were some breakthroughs in theory, but mostly in hardware processing power, that allowed these networks to have many more layers than they had previously, and that's where you get deep layers of these networks. That's what that term is. Deep learning, right? So some interesting properties of the layers in artificial neural network are that the layers, say you're learning to recognize faces, or cars or elephants, chairs. The layers that are closer to the input in the network each unit learns to respond to very simple features or shapes in the image. So first it's just lines or colors or gradients. And as you move through the layers closer to the output, you get more and more complex features that it learns to recognize. Until finally, near the output, you get, for instance, complete faces almost. So a single unit could code for, Matt, right? In theory, if I was training a network to recognize specific people.
That's a lucky unit.
Yeah, totally. And what's interesting about that is that that's analogous to what we see in biological systems. So in our visual system, early on, you can find cells that that are called edge detectors. Then you start finding cells that are moving edge detectors. Then you start finding cells that are kind of shape detectors, like respond to simple shapes, and then so on and so on, until finally, in theory, you have a cell in your brain that responds specifically to your grandmother's face, for instance. So there's some, when you're looking at image-based AI, there's a few things to keep in mind. There's kind of several types or classes of AI models, or visual AI models. The first and the simplest is just basic image classification. You show a picture or an image, and the model gives a single response. The image is either a dog or it's a cat, for instance, right? However, what is it going to do with something like this, right? It's basically going to give the answer of based on, like, if it thinks the image is more dog-like or more cat-like. So who knows what it's going to say, a trained model would say in this case. So the next kind of iteration or advancement in image-based AI was object detection and localization. So that's where we have models that can detect multiple objects in an image and localize them to the image. In this case, we're localizing them with bounding boxes. The one that I'm going to show in my demo, it can actually give you bounding boxes, and it can do what's called image segmentation. So it will show you the pixels in the image which it considers dog, and the pixels in the image that it considers cat. Do you have anything to?
No, this is the cool part.
Okay, so my demo, basically, I do not really consider myself an expert in AI or deep learning or anything. it's just something I've been interested in for a while, and I've kind of tried to follow the advancements of it. And so what I want to get across is that the nature of the research and the level of the tech right now is such that it has a really lower barrier of entry. So if you just spend a little time reading about what's out there and a little bit of time researching it, you can make some really cool stuff with basically off-the-shelf tech. And that's basically what I did here. I didn't need to set up any training pipelines. I didn't actually train anything. I'm just using an off-the-shelf, freely available published object detector network and weights that the author provided. So they spent all the time getting all the data, all the images, and spending a week or two churning through those images, training the thing. I'm just using their knowledge. So this is, it's basically just like really similar to what Matt was describing on your phone, where you have all your photos and you type in dog or suitcase in this case, and it shows you all the images in your phone that have that tag. So it's just a simple web demo, simple web app, searchable by text. That's basically my demo, which I'll show in a little bit. But talking about
that looks good.
Oh, yes.
So this morning, Dustin drew this like in Visio or something, and it looked like a dev would draw it. And so our creative director didn't think that was cool.
He prettied it up a little bit.
He saw it, and he was like, And if you know Seth, you know that when he growls, it's.
So yeah, on our drive over here to fix this up.
Shout out to Seth.
Yeah. So it's a simple web application written in C# using Blazor, which is a really cool web programming framework, which if you're a web dev, I would suggest looking into. It's super cool. And then I have a simple Python gRPC server, which all it does is sits there and listens for messages from the web application, and so the user uploads an image, the web application forwards the image over to the AI server. The server just loads up that off-the-shelf object detection model, loads up the weights for the model, and runs the images through it, sends the results back to the web application. The web application stores the results in a database, and then the user can search. Pretty straightforward. So let's try to do it. Hopefully this is where we hope things don't crash or whatever. But,
it always works fine till you're sitting there.
right. So again, here's the images. Here's underneath each image are the tags of the objects the AI believes it's found in the image, and also along with how confident it is in its decision. So,
where's the carrot?
Yeah, so here's an example of, it's not always right. So it thinks that weird orange, I have no idea what that is, so I would be confused, but it thinks that's a carrot, and it's 93% sure it's a carrot. So it's nice that you get a confidence level, but you can't necessarily trust it. It can be very confident about something and be completely wrong, so it's good to keep that in mind. Oh, and also, by the way, this is a model that was state-of-the-art in 2017. There's already models that would perform both, that would train faster and have more accurate results than this one. So it's good to keep in mind. Yeah, I mean, it's pretty straightforward. You can search, so I can click on a tag, and it will find all the images in my database that it believes have people in them. Right? There's tons of people there. You can.
I mean, it's not wrong.
Yeah, there's a lot of people. This is interesting. It thinks this kind of seal is a clock. I can't really tell what it is. It does look clock-like. But again, and also something to keep in mind, if you're using something off the shelf like this, it's been trained on a finite set of classes of objects, of tags. So if it sees something in the image that it's never been trained on, but it's like something it's seen, it's gonna of course say that's what it is, right? So so this is the tags that my images have and the number of instances of those objects in the images, right? So and you can click on one where it's like bottle, Right, so bottle, yes, there you go. Sometimes it's hard even to see. You're like, well, where's the bottle? Like in this one, there it is. Right, so bottle and bottle. It's like, yeah, that's not a. I think that's like a coffee cup in front of a jar, and then that's like a coffee French press. But it was not trained on French press, so bottle is the closest it can come up with. Right?
Bottle.
So if you're going to use something off the shelf, you have to keep those things in mind. However, though, one thing which I was hoping to do in my demo, but I didn't get a chance to do, is to show off what's called transfer learning. So that's where you take an existing pre-trained model, and instead of training the whole thing from scratch on your data, you can essentially take those pre-trained weights, chop off the very last output layer, put your own output layer on, and train it on your classes of images. And so it has all this knowledge built up in the weights through the layers. It just has to come up with the final decision layer weights. And it can do that much like orders of magnitude faster. So you can train, so training the model I'm using here probably took like 2 to 3 weeks on really powerful hardware. So you can do like a transfer learning task in like minutes. Depending on what you're trying to do and how much.
So like if you said, here's a picture of a sword, and you train it on the sword, you're going to assume, because it already knows all of these things,
it can figure out sword
right,
much quicker. Yeah, it's just like, it already knows about bottles, right? So if I was going to train it on French presses, it can generalize to new things much more quickly than learning it from scratch.
Can you show them the pizza one where it's got it knows the girl?
What was it? I think that was like.
Yeah, that's right. There it is.
Yeah. Okay. That's interesting.
So this one got me really quick because it thinks that guy leaning down is sort of a human.
That's like 74% sure.
But you just see her brow and her eye. It knows that's a person. It's for sure, like it knows. But the guy leaning down with pizza in his face, it's like, could be. I don't know. And the books.
Yeah, also it thinks these boxes of pizza are books. So
but they're like a book with pizza.
The best book, right? Okay, and then I'm just going to show off kind of uploading a new image just so I can prove I'm not totally faking it. Let's see. All right.
That's nasty. Are those yours?
No. These are just it's just a database or just a collection of images I got off of the internet. So if you start doing research on training these models and stuff, an important thing to find and keep in mind are resources for training. And so this is just like a library of images that you can use to train the network. But the network wasn't trained on these specific images. So hopefully, fingers crossed, okay, there it goes. So it's just going image by image, reading them, and sending to the model, and then it comes back with the tags. And then those should be the very first, here's the, so these are the 3 images we just sent out, the first 3. So there's that one, let's see what it says. So yeah, cell phone. What is that? It thinks that person's toe is a remote.
It totally should be.
Yeah. That's it.
That's like snow crash level AI right there.
So yeah. So that's basically my demo. I just want to say, so again, it took me about 20 or 30 hours to make this, but most of that time was, the vast majority of the time was just building the web app, and actually was learning Blazor, because it's the first thing I've done in Blazor, and it was cool. So most of my time was learning the framework. The hooking the AI into it just took like 3 hours maybe. It was the simplest part of the whole
How many of you are devs out there? Okay, that's cool, because he wanted to show the code too, but like, when he shows you how much code was needed to make this thing actually understand the AI, blows my mind.
Yeah, so this is that Python server. It's just 130 lines of code. This portion in the middle where it says load the model. That's a load the model. That's essentially all I had to do. So I again, used someone else's code that's published on it's a researcher's, in code that's published on GitHub. I just import his library, load the model, load the weights that he provides, and essentially make a call that saves that model in memory so you can reuse it over and over again without having to reload the whole thing over again. And then essentially using gRPC, this really cool RPC library, I basically subclass an instance of the server where I provide some methods. And here's the portion of code that actually, once the server receives a message, it just sends it in. The model, we show the model the image. I get a response back, and that just has basically the bounding box and the label data, and I just return that to the web app. So here, let me see a second. Here's the guy's GitHub. He shows off some other cool demos and projects people have done with this model. So this is like a 4K video where in real time, given enough processing power, you can do this in real time. He can run the model on each frame of the video, which is cool. Here's a cool project where someone taught it to automatically detect and label like baseball and soccer and football fields for like a mapping project. Just lots of cool things. Oh, this was a cool tutorial on doing transfer learning with this model to teach it about balloons, right? And then he used that to colorize videos of balloons. Some medical imaging stuff, or robotics. Anyways, there's.
Oh, the LiDAR is cool.
Yeah, this is. I'm really excited about this. This is generating 3D geometry from LiDAR data, which is really cool if you think about it, because it has to implicitly figure out. Well, yeah. Anyways, it's cool.
So last year, about this time, we did a project in-house that was for a defense agency, and part of the thing that they asked us to do was just figure out how we would do what they were asking us to do, but we didn't have data for it. And so this guy goes away on Christmas break, and he used Unity, like the game platform, right, to build. How many screens did you build?
Wow.
Iterations.
Well, like infinite.
Yeah, I mean, so the AI was trying to model on objects in a parking lot. We'll say objects in a parking lot, cars, right, in a parking lot. But they hadn't given us enough photography to handle that. I'm not going to hire a drone guy to go do that. So he just builds as many as he wants to in Unity. So you can take a couple of car assets and you put it on a field and you put them around, and then you start counting, right? And he knows exactly how many cars are in a picture because he just wrote it at the top of it. So the model he trained last year did some really neat things, and it would be even neater with this one.
Yeah, this would be
way
cool
cooler.
at the time. Let's see, let's get back to.
Before we get away from it, can you show them the elephant? You know which one I'm talking about? This morning we found a picture of some elephants that I liked a lot because it takes the back of an elephant and it thinks it's something else, and I thought it was great.
Here it is.
Oh yeah, that's it. So you see that hump of the elephant?
Sorry. There it is.
See what it thinks it is? It thinks it's a cow because it looks like the back of a cow. Why not? It should be a cow, right?
So that's the demo. Any questions about anything so far? Or?
I think you said that you should probably about 2 to 3 weeks for the initial learning on this. It sounds like if you were to say you import those existing weights and everything, and you wanted to add in a new field or start learning, do you have an anticipation of how long that would take? Would it still take possibly 2 to 3, or because of the data it has to work with and extrapolate already, you can shorten that time for a new asset, if you will?
Yeah, exactly. So basically the question is if you want to take the existing model, the existing weights, and learn a new class, how long does that take? Again, it's orders of magnitude shorter, so as little as minutes, potentially. Again, it depends on how many new classes you want to learn and how much data you have. But so the nice thing is that instead of having to do computations through the whole network, which are potentially millions of computations just to look at one image and update the weights for one image, you keep most of the weights static. So you don't have to do anything to them. You're only adjusting maybe 1,000 weights, right, on your final layers. And so that happens much more quickly. So, and typically you need orders of magnitude less data as well. So that's one of the downfalls, or the something to keep in mind when you're thinking about using one of these models or training one of these models from scratch, is to get good accuracy, you're going to need tens of thousands or hundreds of thousands, the more the better essentially, but many examples of what you're trying to learn. But if you're doing transfer learning, you can often get away with maybe dozens, but hundreds of examples and still get very good accuracy.
What else? Carl, you got a question?
What does it cost to buy the software you need to do this?
Oh, good question. It's totally free. So all
The plant comes through.
How much does it cost to what are the licenses on the software? All the software I use for this is totally free, and that's generally the case in this field. It's pretty much all open source.
The processing is not free, but everything else.
Yeah, so actual compute time is not free, and that can be expensive. But there's been a lot of push in the last 2 years on, for instance, instead of saying, like competitions where instead of trying to get the highest accuracy on some task, instead the goal is to, given this base level of accuracy, compete on finding the cheapest, essentially the least compute necessary to come up with that accuracy. So it is getting cheaper and more efficient to train these models.
What else? Yeah.
How many trillions of math operations does it take per image? You said it's expensive computationally.
Yeah, that's a great question. It totally depends on the model itself, but yeah, I mean, hundreds of millions probably in this model, I would say, like hundreds of millions of individual multiplications and adds. Yeah, it's a good question. And again, it just totally depends on the complexity of your model.
Anyone else?
I've got a harder one.
Oh, good, Carl, thanks.
What's the advantage of writing your own software to do this as opposed to just using a service that already provides it?
So that's a really good question. So one advantage is that you can often take advantage of expert domain knowledge in how you custom design your network. So a lot of the times you can squeeze out maybe an extra percentage or two of accuracy if you have someone who knows the problem domain really well and knows how to build these things themselves really well. So yeah, it is possible to squeeze out a few extra percentage points. But that's changing, I would say, actually, in that there's some really cool research over the past like 4 or 5 years called AutoML, auto machine learning, which is essentially an AI or an algorithm that itself, given a problem and given data, it can come up with an AI model that solves that problem. And in many cases, the models it come up with can outperform models, previous state-of-the-art models that humans have built. So that's a promising field of research.
Do you guys know about the Google chatbots? Google had 3 chatbots, A, B, C. They instructed A and C to have a secret between themselves and not to tell E. And A and C developed their own language outside of the Google engineers, to the point where the Google engineers leaned over and unplugged it, because that's scary. So that's not cool. What else? Nothing? Yes, go ahead.
Do you see this one day, or I guess other programs out there already, where you don't have to know how to code, you be able to set up your own model and train it?
No code AI?
Yes, absolutely. And there are some services, some of the big companies, like Google offers some services where, it works really well on some specific applications, but again, if you have some really specific use case, it might not do that well on it, but there are already services like that.
Microsoft's got some good ones. Yeah, go ahead.
If you get it, like say for Sleepy to run results and say a person isn't a person, does it just start tagging things erratically, or does it just stop tagging altogether?
That's a good question, and it totally depends. I guess it depends on the distribution of your wrong tags, you know. So if it's a completely random distribution of tags, like say every time you see a person in your training data, you just randomly choose a tag, then probably I would guess that it would never be confident enough when it sees a person to assign any tag to it. But if in your data you weight it somehow, then it will say whatever it is you've weighted it to, if that makes sense.
It's like you're making an introvert. Sorry, devs. Oh yeah, right there in the.
Is there a correlation?
I'm sorry, I can't hear you.
Is there a correlation between beard length and AI expertise?
Clearly, if it's shorter, it's better. So yes, there is. What else? Yeah.
Did I hear you say Glacier is the software you're using?
Blazor, B-L-A-Z-O-R. It's a C# web programming framework.
Oh, okay.
That so the model that I'm using, it uses a framework called Tensorflow, which is one of the most popular frameworks, computing frameworks that AI people use to make these models. Tensorflow, and that's developed by Google and maintained by Google. It's an open source project. There's some higher level like libraries written on top of it. One that I really like called Keras, and that makes things a lot simpler. Like you don't have, like TensorFlow is almost like, in my opinion, almost like machine language versus some higher level language if you're trying to program AI. Whereas TensorFlow is like a lot more straightforward and more conceptually clear.
These are all based on C#?
Sorry, no, the TensorFlow, I think someone is writing some hooks for C#, but TensorFlow it's like a C++ based library, but almost all development that researchers, almost all use of it is through Python. So there's Python hooks for it that people use. You know. But Python is the #1 kind of machine learning language these days. Back to your question on wrong data, right? So there's been some really interesting things that people have noticed is that, for instance, in one example I was reading about was in some radiology imaging software, right? So detecting cancers or something like that. So even though sometimes, so the network used training data from radiologists' diagnoses, right? So they're like, oh, this is yes, a cancer, this is no, a cancer, yes, no. Even though it turns out after the fact that they realized some of those labels were wrong, the network ended up outperforming the radiologists and got those, given those same instances that were labeled incorrectly, ended up labeling them correctly. So it's like if you think about it, it's kind of like radiologist A makes a mistake here, radiologist B makes some other mistake here. It's like the mistakes are spread out, but the AI, the learning algorithm kind of sees the big picture and kind of sees what the real pattern is, right? So it's interesting that even given some percentage of incorrect training data, the network, these algorithms can do better than you would expect. Like they can do better than the training data in some cases, which is interesting.
So it can potentially learn who the bad actors are that are putting in bad data as well.
That it could, yeah. In this case, that's not what was happening, but yeah, you could. Yeah.
Maybe it just starts to throw away the bad stuff.
Yeah.
Maybe. Yeah.
How common is that, like in the level AI we're working with here, how common is that level of coding for correcting incorrect information?
Oh, so you're talking about, oh, okay, so yeah, that's an important point, which maybe I think what you're getting at is how do you, like in those cases where we're like, oh, that's wrong, right? When we're looking at the demo and we notice things that were wrong. Is that right?
And the AI is noticing it itself. How common is that level of coding in the AIs at this point?
It's a pretty common phenomenon, and it's happened in things I've worked on myself where I would be looking through and I'm like, oh, well, that's wrong, you know. But then I look closer and I'm like, oh, wait a second, like, no, it's right. So that happened to me when I was doing a system that would classify courthouse documents, and it was looking at even really, really old courthouse documents from like the late 1800s that are like handwritten and stuff. And anyways, so the data was pretty bad and noisy sometimes. And so just at first glance, I would think this thing was a oil and gas lease, but it ended up being, but the model's like, no, mineral deed. And I'm like, no, that's wrong. And I look closer and oh, sure enough, it's a mineral deed, right? So it happens a lot.
I know we're tight on time, but could you describe again, real quick, because I think it kind of goes to his question.
So there's a class of AI models called Ganz, which stands for Generative Adversarial Networks. And if you've seen any of the new stuff with like deepfake or just where these AIs are generating synthetic data, right, like making faces from scratch. So those are really interesting and a huge push. There's a lot of research going on right now. And the way they essentially work is really interesting. It's you have two networks, two models that are essentially competing with each other. One is trying to, for instance, make pictures of human faces, and the other network is trying to guess whether it's a real image or a synthetic image. And based on that, it's like a competition. So it makes a face, and this is like, nope, I can tell it's fake. And so it based on the error gradients based on basically why the discriminator knew it was a fake, it kind of feeds that information back to the generator network, and the generator network can improve, right? So that's how those work, and it's pretty cool. I don't know, maybe we can find some examples.
They're super fun. Anything else before we have to like release the room? Nada?
So, for instance, these faces are synthetic. These are not real people. Like they've never been alive. There's never been these people living, right? But it's totally, you know, it's pretty impressive how good their Ganz is using.
Real quick, can you throw up the one where the guy doodles and it draws the, I know we're walking out, but.
I think this is it.
It's just that picture Anyway, there's a picture of this really bad, clearly someone drew it in paint, waterfall in Vista, and the AI turns it into this just stunning view of like, some Hawaiian waterfall. There you go, but it never existed, that's not a picture. You doodle this bad thing over here and the AI goes, cool, watch this.
And so this is also based on a GAN, which is a generative network.
Wow.
In other words, don't believe anything.
And so I think you can start to see some of the potential, it's just kind of still in its infancy, but for content creators, artists, graphic designers,
VR.
Yeah, VR, like movie effects. It's going to blow that wide open. I think that field. It's going to change it dramatically. Yeah.
What's that gonna do to copyright laws?
That's a great question. I don't know.
Yeah.
I don't know who gets the copyright on these things. I don't know.
Yeah. Nothing over there? All right, thanks.